Anybody have any idea what free fall is? What do you think free fall? There's a song, Free Fallin' by Tom Petty. What's happening?
You should play it.
I should. I should have. Too late now. What's free fall?
Something is falling down, not at a constant acceleration.
You think not a constant acceleration? Okay.
Well, no, because if you fall, that's just more amount of time for the force of gravity to pull you down.
Okay.
That's why you say if you drop a penny off the top of the Empire State Building, it can kill somebody.
That is, yeah, so there was a Mythbusters about that, I don't remember.
I thought it was a myth because of air resistance and
Yeah.
aerodynamics of the penny.
Okay, so so air resistance is an issue when you're falling from lots of great heights. We could talk about that in a little bit, but the word free fall just means that it's something with only gravity acting on it. It's the only force, right? And remember that the force due to gravity is what?
9.8.
No. What is the force due to gravity? Starts with a W.
What?
No, what does start with a W, but that is not, it sounds a little bit like what? Watt? No, watt is a unit of power. What? Weight. Yes. We were getting there. Okay. Weight. Good. So, when we talk about free fall, we are talking about a situation where only gravity is acting on it. So, that means that if you are in a situation like dropping a penny from the Empire State Building or skydiving, things like that, where air resistance is a really, really big deal, okay, that's not officially free fall, okay? So just in this course, we didn't really have time to do a full thing on air resistance, but I have an ed puzzle if anybody's interested on this skydiving one. So, but air resistance is an important thing when we're talking like in our daily life, right? Like, why does this fall relatively slowly, right, compared to that, right? And that's because this piece of paper is pretty, has a pretty low mass, okay? And so air resistance is going to affect this more. So that's how you know that you're dealing with air resistance. Yes?
So, where is it possible to achieve free fall? Like, is it even possible to?
Yes. So where is it possible to achieve free fall? It needs to be in a place with no air. And actually, I'm going to show you some videos today.
Wouldn't you die?
Well, yes, I don't suggest that you in particular are there without any protective equipment, but I will show you 2 videos where you will see actual free fall. Okay? So,
Isn't it just at a standstill?
you think that things, if there's no air, that they'll be at a standstill?
Well, no, in free fall, it would look like it's just standing. It would look like it isn't moving.
Why?
I don't know.
Gravity.
I was asking a question.
Okay, then no.
Okay.
If things are and I will tell you that this is a very decent approximation for free fall. The amount of air resistance that this thing is experiencing is very, very small compared to its weight. Okay? And so when we talk about free fall, we're going to talk about situations like this. Okay, where I'm just dropping a thing and letting it roll across the floor because I really didn't want it anyway, right? Yeah, well, Annika's going to throw it to me. Thanks. Okay, so I keep dropping this, and that is free fall. Is everybody cool with that? If you think about what this thing is experiencing, it is experiencing a force down due to gravity, and basically that's it, once it leaves my hand. All right? Is that free fall? I threw the ball up. After it left my hand, was that free fall?
No.
You say no. Ava, you're shaking your head. Why do you think it's no? You think because it's going up. So, Malia? After it left my hand, was there a force? Maybe. Okay. Siri?
Like you gave it energy, like you pushed it up
I, I did. And then once it left my hand, was there any more energy being given? No. Once this leaves my hand, it is in free fall. Because the only force on it is gravity. Let's think about that a little bit more carefully. When it is traveling upwards, what's happening to the speed? Joseph?
It's decreasing.
It's decreasing, it's slowing down. So everyone point in the direction of it moving when it's going up. Everyone point. Right? It's moving up. So it is moving, right? It's moving up. And we just said that on the way up, it's decreasing. The speed is decreasing, it's slowing down. So which way do you think the acceleration is going to be? Right? Remember that velocity and acceleration are in the opposite directions. That means it's slowing down. So if the acceleration is down, what force is causing that acceleration? Gravity. And gravity points which way? Down. What does down mean?
Yes.
Yes.
There's no certain direction that down could be. It could be lower.
What's the definition of down? What is that? Have you ever thought about that? What's down?
Subjective.
It's really not. Yeah?
The earth.
It's towards the center of the earth. That's exactly right. Right? Go to Australia, down is just towards the center of the earth. Toward the center of the earth. Because that's how gravity works, right? Is that things are drawn to the center of the earth. Okay? I mean, obviously, if you talk about universal gravitation, they're drawn to, other large planets and things like that. But for right now, this is what we're worrying about. Okay, so as this thing goes up, it's slowing down. The acceleration is down. Velocity is up. Okay? What happens when it reaches the top? Yeah, Joseph?
The velocity stops.
Yeah, it has to go through zero, right? At the very top, the velocity is zero. Okay? But it's still being pulled down. And so what's happening to the speed as it goes down? It does. It gets faster, right? That's just like this part. Whee! Right? It gets faster. And so everyone point in the direction of it moving down. Now it's getting faster. So what's the direction of the acceleration? Also down. The acceleration is in the direction of the net force. So that downward force, that's gravity. Okay? Okay. Remind me what weight is. To actually calculate it. It's been a while, but we did this at some point. Wait. Do you remember?
Yes.
You were waving? Yes? Sorry, who was? Yes?
Isn't it the force of gravity times the mass?
It is the force of gravity. I'll write that here. Okay, but how do we actually calculate it? If I know I have a certain mass on Earth, and I want to know its weight, what equation did I use? Yeah?
9.3 meters per second squared times however the mass.
Okay, it was equal to mass times the gravitational field strength. Right, that was little g.
What is the gravitational strength?
So on Earth,
Is it 9.3 or
9.8, little g is 9.8, and the units were Newton per kilogram. Interesting.
Yeah, well, it's the
Okay.
same thing.
Newton per kilogram. Okay, so this force due to gravity, right, in free fall, if you were drawing a picture, it just looks like this, right? That's the only force on it. And so this force is going to be equal to the net force because it's the only force on it. Does that make sense? Okay. So we're getting there. We're going to bring back Newton's second law in a second, but I just wanted to remind you that weight, right? In terms of like stuff that appears in your table of friends. Do you guys have your table of friends? Do you have weight?
Weight is units,
Right, so weight. What was the variable for it? Oh, I just wrote it.
right? W.
Nope.
Oh,
F sub g, because it's the force due to gravity, right? And what were the units? Newtons, because it's a force. And then we had gravitational field strength. Is that also in your table of friends?
Somewhere.
Yeah,
You might have it written as little g,
it's G and then N.
and it's little g, and it's newtons per kilogram. Yes,
Can we just write meters per second squared? Will you take either or?
I will. It is also equal, as we just mentioned earlier today, that a newton per kilogram is also a meter per second squared. Either one of those is fine if you want to write for little g. And I'll talk, at the end of all this discussion, I will talk about sort of the bigger idea there. Okay. How are you feeling? We're good so far? Yeah? Angelina, what can't you read, sweetie? Do you want to come back up? Then you can read.
No, it's just like thinking.
What? So, what is the weight of a 0.3 kilogram apple on Earth? And I'm going to throw, one of our boxes here. Whee! Right? Like at this point, you see that box and you know what to do, right? No? Still no? Oh, I'm going to cry. Okay, if you don't, then please come get help before the final. Yes, Isaiah.
I know the answer.
Uh-huh, that's nice. This is one of those problems that I actually care about doing the work, right, before I care about the answer. So, what's the first thing we write, Matthew?
What?
Huh? What's the first thing that we write in here?
The nose,
Okay, what you got?
0.3 kilograms.
Okay, what is 0.3 kilograms?
The mass.
The mass. What variable is that? M. Perfect. All right, what else do we know? Lola.
The gravitational field strength, which is 9.8 Newton per kilogram.
Very good. And you knew that because it said on Earth, right? Fantastic. And what are we looking for? The weight. What variable is that? FG. Awesome. Now, what equation do we have? So I just wrote it on the previous slide in words, but I didn't actually write like,
Fg equals G times N.
okay,
Fg equals little G times N.
mg is how we write it, just generally, mg, okay? All right, now we just plug a Rooney, and we will let Isaiah tell us the number.
2.94.
Is there anything else you want to say?
Fg.
Nope. What are the units? Newtons. Okay. That is the weight of a 0.3 kilogram apple on Earth. Yeah? Remember how to do those now? Cool. All right, I have some questions. So, I'm going to hold the apple. Okay? So let's talk about this situation. I'm going to draw an apple. I know, it's exciting. Oh, look, it's kind of like an apple. All right? I said hold, but just kidding, because I can't draw a hand. So all of a sudden now, oh, it's on a table. Yay. Okay.
Whoa.
That works. All right. What kind of forces is this apple experiencing? Let's hear from the new people. Joseph, sort of new. Okay, yes.
Rock comes from
I know.
gravity.
Gravity. Which way would that be pointing?
Down.
Down. That's right. It's always pointing down, right? So F sub G, and did we just calculate that number?
No.
What's that?
Yeah.
Yeah, right? It was like 2.94 newtons, because I'm just going to write that, okay? Sound good? Okay, what other forces does this apple experience? Maddie? Yeah, it's the force going up from the table, right? So the force, I'm going to write like F sub table, right? Just because, right, it's a force that the table is exerting. By the way, when you go on in physics, you'll find out that that word, that force has a special name. Does anybody know?
Nope.
It's called a normal force. So, support force or normal force. So, what do you think the size of that, how hard do you think that table is pushing up?
About the exact.
Yeah, 2.94, right? Because what's the net force here?
What?
It's in equilibrium, right?
Yeah, static.
There you go. So it's in equilibrium.
Static.
I agree. Static. Because it's just chilling on a table, right? Oh my goodness, that says equilibrium. Sure it does. Equilibrium. Okay, it's in static equilibrium. So, right, you guys just did a bunch of problems where you're like, oh, look, here's a thing. It has a force this way. It has a force this way. They're the same size. The net force is 0. Good stuff, right? Cool. So the net force of that guy on that guy is 0. All right. What? What's wrong? Can you see? Okay. Now, I want to talk about dropping the apple. Okay? What's that? Okay. Apple. Wee. All right, now what forces are on it?
Just gravity.
Just gravity. What's wrong? All right. Modest too. Okay, if you drop the apple, what is the net force on this apple?
9.8 kilonewtons.
Nope.
Oh.
Look at the picture. If you had that on your quiz, and you had an object with 2.94 newtons on it, and I said, what's the net force on it? What would you say? 2.94 newtons. Okay? So, if that is the net force, does everybody see it? Like, there's just one force on it, and that's the whole thing. Okay? That's the net force on it. If there's a net force on it, what do you know that it's doing?
It's more than likely moving or accelerating.
It's accelerating, right? Because this net force is down, right? And so it's accelerating down. Does that make sense? If there's a net force down on it, you know that it's going to accelerate down. That doesn't tell you it's moving down, right? It could be moving up, but if the acceleration is down, that means it's slowing down, right? Okay? Okay. So why don't we actually calculate it? Let's calculate it, shall we? Dude, let's do it. I know you want to.
What am I finding?
So I'm going to ask, what is its acceleration? Right? We just said that the F net was 2.94 newtons, right?
Yes.
And I want to know the acceleration, right?
Yes.
What else do I need?
Mass.
Yeah. Anybody remember the mass?
0.3.
It was 0.3 kilograms. Okay. What equation do I need to calculate the acceleration from a net force? Malia? That's right.
I got it.
Okay. keep it to yourself for a second.
I know.
2.94 newtons divided by 0.3 kilograms. What is it?
9.8 meters.
Yeah,
Oh,
so I,
whoops. 7.345.
Uh-huh. so it's 2.94 divided by 0.3.
Yes.
Yep. It is 9.8.
Oh, she can say it.
And what are the units?
Newtons per kilogram.
Meters per second squared. It's an acceleration, right? You guys,
I want.
oh my God. Oh my God.
I want newtons per kilogram.
So if someone asks you for an acceleration, generally you're not going to give your answer in Newton per kilogram. Joseph.
Just
If something's falling in a vacuum,
Yes.
it's always going to accelerate at 9.8 meters.
Yes. So guys, this value
oh, that actually makes a lot of sense.
is often called the acceleration due to gravity. So most other teachers, when they introduce to you little g, they call it acceleration due to gravity. Okay? And so almost every other teacher you'll ever meet says that. I introduce it as gravitational field strength because it is. It's a field. Then that's because there's a bigger thing at play here. But most people just talk about 9.8 meters per second squared as the acceleration due to gravity. But you can see that it's actually, right, you're like, wow, why is it that same value?
Because it's the same thing.
So let's actually see what happened. And then we'll watch some videos. Okay, check it out. So, in general, the acceleration is net force over mass, right?
Yes.
In free fall, what is the net force? In free fall,
Oh, is
there's
it-
only gravity acting. So the net force is just the force due to gravity, right? Okay. What's the equation for the force due to gravity?
F times m.
What's F sub g?
Say that again?
What's F sub g? You did just write this.
9.8.
No, read the formula from the box from 2 boxes ago. What? It is. And so it's equal to mg. Hey guys, what happened?
I don't know. Isn't it?
The m's canceled.
No, I want numbers, Miss Ryder. I don't get it.
Yay! Much fun.
Yeah?
I want numbers.
Okay, you want numbers?
Yes.
Okay. What was it? It was 2. Where did we get 2.94?
That was the weight.
It was 0.3 kilograms times 9.8 newtons per kilogram divided by 0.3 kilograms.
Okay, that makes more sense.
Do you see? We took the 0.3 and we said that's the mass. So what's the weight? Oh, I'm going to multiply it by little g. And so I got that 2.94. And then I divide by the mass because I'm calculating the acceleration for Newton's second law.
Why did you put mass over FG? Or why did you put mass times FG over mass? What do you?
Where do you see that?
The equation you just wrote.
That's little m times little g,
Yeah, I know. Why would you put mass? Oh, never mind.
right? Remember that the definition of weight is
Yeah.
is Fg equals mg.
Yes.
So guys, this is big. What this says, what this says is that every object in free fall has the same acceleration independent of mass. That's cool. But why does it make sense?
Why does it make sense? Because it would have to, otherwise it wouldn't be.
Okay. So if I have a bowling ball, it has a huge weight, right?
They'll go the same speed.
But, hold on, it has a huge weight, but it also, because of its big mass, has a big what? What's the word that's associated with mass that starts with an I? Inertia. So you've got a bowling ball with a big weight, right? A big force on it, but it also doesn't want to move, right? Because of its big mass. So those two things cancel out. That's how that's working, is because something that has a bigger weight also has a bigger mass, so more inertia. Make sense? Let's watch some videos.